Okay, so it's recording now. Welcome everyone to part 2 of lecture 8. We were discussing polarization of light, and we were using the language of electric field. And now we want to interpret these results as in terms of photons. Okay, so Um, we know how to relate the intensity of the outgoing light from the second polarizer with the outgoing light from the first polarizer. So the intensities are I and I naught, respectively, and they are related by this equation here. Okay, so now that I want to phrase things in terms of photons, as I said, when I pass light through the first polarizer, I would say that the photons that uh, uh, are on the other side of the polarizer, namely those that pass through the polarizer, they will be polarized in the theta direction. Okay, so I will say that each photon will have the same polarization. Even if this is difficult for you to imagine what is the polarization of, the photon, which we view as a particle, this is a terminology that we use. Um, and what we have discussed in previous lectures last week is that the intensity of a light beam is proportional to the number of photons. So the intensity that appears here, which in the electromagnetic wave picture is proportional to the square of the electric field, in the photon language um, it is proportional to the number of photons. So when I say that the intensity of light has decreased, I am saying that less photons passed. Okay, so if I had some quantity of photons before the polarizer, I'll have less photons after the polarizer because some of them will be absorbed by the polarizer. So this equation here, okay, if you think about photons, can be interpreted as follows. If I take I naught to the other side, write I divided by I naught, this is the fraction of photons that pass through the two polarizers. Okay, so after the first polarizer, I will have some amount of photons, but after the second polarizer, I will have a new amount of photons, I, and I divided by I naught is the fraction of photons that uh, were transmitted by the second polarizer. Okay, but as we discussed, you don't transmit half of a photon. Either the photon passed through the polarizer or the photon did not. So you don't say that a component of a photon passed through, as you say for an electric field. Okay, you say a photon passed or the photon did not pass. Okay, so when I tell you the number of photons that passed and divide it by the total number of photons that were before the polarizer, what I'm giving to you is the probability of finding of the photon to pass. Okay, so this is just a calculation of a probability. So what this equation is showing to you is that I divided by I naught is the probability that if, so be careful with what I'm going to say, is the probability for a photon that is polarized in direction theta due to the first polarizer cross the second polarizer in direction phi. So this is how I interpret this equation in terms of photons. I divided by I naught gives you a measure of the probability that a photon polarized in the theta direction will pass through a polarizer with direction phi. Okay, so what I'm saying is that after the second polarizer, I will have photons that are called photons polarized in the phi direction. Before the second polarizer, I had photons polarized in the theta direction. So I want to answer the following question. What is the probability that I will see a photon polarized in the phi direction if it was polarized in the theta direction? That is the question that we want to answer. And the probability is going to be cosine squared of the difference between theta and phi. Okay? So let me check the chat. Can we say that polarization is yes, yes. So in the picture of waves, polarization is nothing but what you wrote. Okay. Now I will introduce some important terminology that will be used all the time in quantum mechanics. So at the classical level, we say that a system is in a well-defined state, okay, when we know the position of all elements of the system and the momentum of all elements of the system. So the simplest system you can think about is a particle. So in classical mechanics, you say that you know the state of the particle if you know the position of the particle and if you know the momentum of the particle. Okay? This is all the information that you need in order to solve the dynamics of a theory, in order to solve the dynamics of the particle, because these will be the initial conditions of your differential equation that you're going to solve, which is Newton's law. So in the same way, we want to use this name in quantum mechanics, and we are going to say that a photon is in a well-defined quantum state, so we are talking about quantum mechanics now, of polarization when we know that is linearly polarized in a given direction, theta or phi. So after the first polarizer, we say that the photons are in a well-defined quantum state of polarization theta. After the second polarizer, we are going to say that photons are in a well-defined quantum state of polarization phi. Okay? And what we want to compute is the probability. Pay attention to the sentence that I'm going to say. I want to compute the probability of getting a photon in a well-defined quantum state of polarization phi if it was in a well-defined quantum state of polarization theta. Okay? This is uh, 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 what I want to answer. This is what I want to understand in this system. So we can say that the first polarizer, the one in the theta direction, prepares photons in the state of linear polarization theta, because after passing through it, we say that the photons are in a well-defined quantum state of polarization theta. And after passing through the second polarization, we say that the photon is in the state of polarization phi. Okay? So the polarizers, they essentially define the state of polarization of a photon. And this state is a quantum state. It's the state at the level of quantum mechanics. Okay? So, as I said, the probability of finding a photon prepared in a state of linear polarization theta to pass by a second polarizer which selects photons with polarization phi is given by this expression. Okay? So if I want to ask you um, what are the chances of, what are the chances of seeing a photon here in a state of polarization phi after passing through this polarizer here, which prepares the photons in polarization theta? Well, the chances are cosine squared of theta minus phi. Okay. So phrasing in a different way, if theta is equal to phi, let me ask you, and you answer in the chat. Okay. If theta is equal to phi, what is the probability of finding a photon here in this region in a state of polarization theta 1, right? So if the angles are the same, then the probability is 1. Namely, all the photons that you see here are photons in a state of polarization theta. Okay? But now, if I rotate the angle phi in such a way that it forms 90 degrees with theta, I ask you, what is the probability of finding a photon in this region with a state of polarization phi? It's simply 0. So no photon, if I prepare photons with polarization theta and phi is orthogonal to theta, there is no chance for the photon to pass through the second polarizer. Okay? So I hope this is clear to you.
Hello.
Yeah.
Please, what about K? Is K reflected photons or what?
K is just the direction of propagation of the wave.
Oh, okay.
It's the same as in the as the axis z.
So if the angle phi is said that is orthogonal to theta, we always have probability of 0.
Yes. So um, as I said, in quantum mechanics, we are computing probabilities, but there are just two situations where you can say things with absolutely confidence. Is when the angles are equal, then you say that all photons that are here will pass through, and when the angles are orthogonal, that you say that all photons with state theta will not pass. So this you can ensure about the photons. But if phi and theta are such that they are not equal and they do not form 90 degrees, then you can just say that the probability that a photon in this region will pass through this region is cosine square of theta minus phi. Okay? Okay, so now we are elaborating about that. So, okay, there is something in the chat. Okay. Uh, okay, so now we understood that we can compute the probability of finding a photon in some state, given that the photon was prepared in another state. And this is just this cosine squared. But let's look at this expression here in more detail. Well, you see that, well, this is elementary trigonometry. So the cosine of theta minus phi I can write as cosine of theta times cosine of phi plus, because this is a minus sign, so plus sine of theta times sine of phi. So I'm just rewriting the cosine of theta minus phi as this sum of the products of cosines and sines. Okay, this is just an identity that you probably know. Are you familiar with this identity? Okay, good. So I can write this in a even more fancy way. I can write. So someone said is not familiar with this identity. So this is the trigonometric identity of a sum, or in this case, the difference of two angles. So you can relate the cosine of the difference between two angles with cosines and sines of the angles that you are including here. And this is the relation for cosine of theta minus phi. This is something that you can prove, but I mean, I don't have time to do that. But if you're not familiar with that, just take this as being true. And this is just a way of relating the cosine of the difference between two angles and the cosine and sines of each of the angles that you are looking at. Okay? Um, good. So now this product of factors here being summed can be written as a term that just contains information about phi and a term that just contains information about theta. And these I can arrange in the form of vectors. Okay, so I can write this column vector which contains cosine theta and sine theta, and I can collect phi being in a row vector which is cosine phi and sine phi. Well, you could exchange the orders, but this particular order will be convenient as we're going to see. So so what, right? I mean, you are just writing a bunch of things, but what does this have something to do with what we are saying? Well, you see that the photons after the first polarizer, they are polarized in the theta direction, and I have an object here, which is this column vector that contains information that is related to theta. Okay, and this vector here contains information about phi. Okay, so I can make a description of the probability just by looking at objects that contain information of each polarizer. Or, I mean, phrasing this in a better way, that contains information about the photons after the first polarizer and the photons after the second polarizer. Okay. So with this example in mind, I will make a definition. So when I say I will make a definition, it means that I'm going to declare something about some entity, and it is going to become clear what I want to mean by that at some point. So don't freak out at the moment. Okay. So we talked that we want to define a quantum state. Okay. So a quantum state is an object that contains the information that I need to describe a system at the quantum level, as the classical state was the set of quantities that I needed to describe a classical phenomenon. So I will define a quantum state that will have a specific name, and this name is a state vector. Okay, so in quantum mechanics, the state of a system or of a component of the system is defined by a vector. And this vector is something very abstract, okay? That in this case is something very simple, but it can be very complicated. So when I say vector, you don't keep in mind the classical physics meaning of vector, which is an arrow that represents a physical quantity in some direction in space. When I say a vector here, you have to think about a vector as an element of a vector space. And this can be a vector space that is very complicated, okay? But for the system that we are interested on, which is the polarization of light, this is a very simple vector space, which defines its elements as being these column vectors with two entries, okay? So I'm defining a quantum state, okay, as being a vector, a column vector that contains two entries. Okay, this is just a definition. And there is a further requirement that is going to become clear soon, that the sum of the square of C1 and C2 is 1. Okay, this is another requirement that I make about my quantum state. So the quantum state is described by a vector, by a state vector, such that the norm or the size of this vector is 1. Okay? And as we are going to see, this condition of c squared plus c1 squared plus c2 squared equals to 1 is going to be necessary because, as we just saw, the probability of finding photons with polarization theta, if they were polarized with polarization theta, is 1. That's why you have this 1 here. But this is going to become clear later on. Okay? So this condition is called the um, normalization condition of the state vector. Okay? So far, I didn't say if C1, what are C1 and C2. So I'm treating them as real numbers so far, but they can be complex numbers, okay? So C1 and C2 can be complex numbers as well, and we're going to see that. So when I talk about a state vector in quantum mechanics, I'm starting with this very simple system where I can use column vectors of two entries, and these entries can have complex numbers. Okay? So let me check the chat. What about vector with more than two entries? Well, when you describe a general system in quantum mechanics, this vector will have more than two entries. In fact, it can have infinitely many entries, okay? But for this system that we are going to discuss, which is the polarization of light, it needs just two elements, okay? But we are also going to discuss systems with infinitely many entries, okay? We're going to get there. Is it the total probability? So for the moment, we saw that in the previous slide, right? So the probability of getting a state with polarization theta when it's polarized in the theta direction is 1. So this is an identity that we saw in the previous slide. And what I'm saying is that this condition here is necessary to ensure this property, but this is not, you don't know that yet, okay? I didn't explain why, okay? then the state is not a normalized state. I don't understand, Felix, what you mean by that.
Yeah,
Uh,
hello.
hello.
I think she asked that what if the probability of theta is zero, and she just changed it to
Ah,
one. So I think she wrote
okay, okay,
a wrong question. So, but I want to ask a question.
okay,
This
okay.
is when you find the norm. I mean, when you find the absolute of that and get one, does it mean the probability is one? I mean, the normalization, is it related to the probability, or is because when you take the absolute and you square, you get one? That is what I want to know. Or there is a relation between that and the probability of the state.
Yeah, you see that when I give you a state, um, typically what I want to discover is what is the probability of a system that is in a given state to be found in a different state, right? That's think about classical physics. You have the initial position of a particle, and then you compute uh, uh, when the position of this particle will be that one. Okay. In quantum mechanics, I have an initial state, and I want to compute the probability of finding this system in a different state. Okay. And what I'm saying is that sometimes the probability for that to happen is 100%. So as we saw for photons polarized in the theta direction, and when the second polarizer is also in the theta direction, then you're going to find photons after the second polarizer with polarization theta with 100% of confidence. But of course, um, since we're talking about probabilities, we know that probabilities must not be larger than one. And this normalization condition will be very important to preserve that. But this will become clear later on, I hope. Okay. Um, okay. So now that I have explained to you what a state vector is, and that we are looking at this particular system where the state vector is a dimension 2 column vector, I want to, okay, maybe a comment. So these systems where you just have states with two entries are called two-level systems, okay? And um, so this is exactly what you need in order to learn about quantum information or quantum computing. You in information and quantum computing, you're going to deal with this type of states of vectors that have two entries. Okay, so this is also sometimes called a qubit. So this is a quantum bit of information. But you're going to be more familiar with that. Okay. Okay, there is a question. Uh, if you have yes, what you wrote is correct, but we don't know that yet. Okay, I'm going to get there, but you're right. Okay, so now I will, instead of writing the state using this column vector notation, I want to save space in my piece of paper, and I will call the state with two entries with a special notation. And this special notation is due to a physicist called Paul Dirac. And the notation is the following. I will define, so this is a definition, okay? I will define the uh, quantum state of polarization theta as a column vector with two entries, and the first entry will be cosine of theta, the second entry will be sine of theta, so this is a definition, and I will call this state, so this vector, I will call this, I'm going to use this weird bracket here, so I have this bar, theta, and this, I don't even know how to describe it. This is a funny bracket, okay? So this was introduced by Dirac, but you can think of this, well, in classical physics, you call a vector something like V with an arrow on top of it. So instead of writing a vector as the name of the vector with an arrow on top of it, I'm just writing the vector as this, okay? So this is just a notation for the vector. And now we can, so this is, as I said, this is the state vector associated with polarization theta. And you see that this state vector appeared here, okay? So now I want to define a state vector that corresponds to this row vector. But this is a column vector, and this is a row vector. So I have to be careful because these are different objects. So what I want to write is not quite a vector in the sense that of a column vector, but in the sense of a row vector. So these are different objects, okay? So instead of writing, I could just write, this. But this, following this notation, would give a column vector of this type. But this is not what I want. I want a row vector. So in order to represent that I'm talking about a row vector, I just use this notation where I just, I just write the vector, but now I write like that. So this represents now this vector here, which is a row vector with entries cosine phi and sine phi. Okay? So if I write theta or phi like that, I will have column vectors with entries cosine theta and sine theta, cosine phi, sine phi. But if I write this and this, then I'll have row vectors with entries cosine theta. So it's like the transpose of the vector, okay? So let me start giving you some terminology. So this vector that represents the column vectors is called a vector state, okay? So the vector state will be this thing. And these row vectors are what we call the dual of these vectors, okay? So this is a dual, okay? But now I can take the product of a row vector with a column vector. And we represent this product as this notation here. So I take these and I multiply by these. So you could think that let's say the appropriate notation would be this, phi with theta, right? So this will be the product between these two things. But in order to simplify, instead of writing these two bars, we just collapse it to one bar, okay? So this is the notation that we are going to use. And in order to understand Dirac's notation, let me just tell you that these vectors have names. So the column vector that is represented here with this funny bracket here is called a ket. Not cat, not cat. but ket. Okay? So this vector, which is a state vector, is a ket. And this vector, which is the dual vector, is called a bra. Okay? And when you compute the product of these two vectors in the order of row vector times column vector, you know that you're going to get a scalar. So you're taking two vectors and extracting a scalar. So this is a scalar product. And this was the joke that Dirac made was the following. When you take the inner product of the scalar product between a bra and a ket, you get a bracket. But of course, there is a missing C here. So the C, I mean, I think Dirac did not want to call this, I don't know how even to pronounce that. So when you take the product between the bra and the ket, you get a bracket. So it's written here, the bracket. And this is the scalar product between these two vectors. And look, I mean, if I take the product of this row vector with this column vector, I will multiply this cosine phi with cosine theta, and this will produce this term here. If I multiply sine phi by sine theta, I will produce the second term here. So when I take this product, what I obtain is cosine of theta minus phi. Okay? So when I compute the bracket or the inner product or the scalar product between these two state vectors, or the state vector theta and the dual state vector phi, I obtain cosine of theta minus phi. So far, so good.
Yeah,
There is a
hello.
question. Yes?
Please, I'd like to know the choice of your bra and the kit. You made the first one. You made the the theta, the kit, and
Yeah.
you made the phi, the bra. Yeah, yeah.
Yeah.
So I would like to know if I choose to make the bra, the theta, and make the kit,
Mhm.
the phi, would that affect my results?
Yeah, so that's a very good question. And as we're going to see, I'm choosing this order because my experiment has an order, right? First, I go through the polarizer in the direction theta, and then I go to the second polarizer in the direction phi. And that's why I have chosen first as the ket theta and phi as the bra. Okay? And you could just inverse the order and come now in this direction. And you're going to choose different objects. So the ket would be phi and the bra would be theta. And whether it is going to affect the result or not, I'm going to tell you in a bit. Okay? Good. Okay, so far, what we did. I don't want you to get lost with equations. So we started with, so it means that the bra comes after the ket. Now, be careful with that, okay? I'm not saying that, I didn't establish any rule for that yet, but we are going to understand what is the meaning of the bra and what is the meaning of the ket. But I was just telling Felix that there was a reason, the reason that for my choice of the bra and the ket was related to the experiment, but we are going to understand what does it mean in fact. Okay. So then there is a comment that in general this scalar product is commutative. For real vectors, this is true, but for complex, this is not. Be careful. Can we have a state that is a matrix? So there are complicated states which they are called tensor product states, and then you can have matrices. Yes. Okay. Okay. So just a short recap. We have introduced the notion of the probability of finding a photon in a state of polarization phi, given that it was in the state of polarization theta, and this was cosine squared of theta minus phi. And then I'm just discussing a bit of trigonometry. So I'm just writing cosine of theta minus phi as this sum here. And I just realized that, in fact, I can decompose this as a product between a vector that contains just information about theta and a vector that just contains information about phi. And then we moved on, and I defined that a quantum state, a vector state, for this two-level system that we are going to discuss is a column vector with two entries. And these entries are not completely independent because they have to satisfy this formula here. And now for the system that we want to describe, I defined the state of polarization.
Sir, I have a question over there for you. Thank you very much.
Sorry, you have a question about?
About the Brian Ket. I don't know if they obey swapping. You can swap them.
If you can swap in the sense of writing this as being theta and phi?
Yes.
So for real vectors, if you swap the order here,
Something like swapping to get Ket Bra.
so you mean something like that?
Yeah, something like Ket Bra.
Yes, you can, and we are going to discuss that.
Okay. Then, if that's the case, then how would the matrix look like?
Then what?
I think the bra is. Let me repeat. The bra is a row vector, and the ket is a column vector.
Yes.
So that one is going to give you something like a scalar.
Yeah.
But
So this
if I swap the ket and then the bra,
yes.
I don't know what is going to happen. I mean, the kind of vector composition you get.
Okay. So
Yeah.
yes, you are absolutely
If,
right.
if we have to still maintain the row and then the column form of it.
Okay. So
I'm
if you
actually
do,
interested in the row aspect. Yeah. The row aspect. I don't know if we have to maintain it or take them as
okay,
they are.
okay. Let
Yeah.
me reply to that. So when you take this particular order of uh, phi and theta appears as bra and ket, you obtain a scalar. So this is a scalar product, and everything is fine. But now, if you take the order of being ket times bra, then this is not going to give you a scalar. It's going to give you a matrix. And we're going to discuss what is the meaning of that. So for the moment, just understand that if you want to extract a scalar, then there is an order. It must be a bra, then a ket. Okay?
Okay. Thank you very much.
You're
You can
welcome.
proceed.
Yeah, so then Mahmoud is saying for complex vector, no, I think he's referring to the fact that if I write bra theta ket phi, this will give a different result from bra phi ket theta, and that's correct. Okay, so I think I have replied all the questions in the chat. Okay, so just finishing the recap, then we have defined the state vector of polarization in the theta direction. So I think my camera is not working anymore. But anyways, okay. Then phi and theta, they represent the state vectors of polarization, but as I said, they have different meanings in the sense that in this expression they appear as vectors, but one is a column vector and the other is a row vector. So we use the notation of bra and ket in order to differentiate them, and we
Hello.
learned how to compute.
Hello.
Just sorry, let me finish just this sentence.
Okay. Okay. Okay.
And we took the scalar product between phi and theta, and this in this order gives you a scalar. Okay. Yes, please. Your question.
Please, is the bra and ket having something to do with Hermitian conjugate?
Yes. Yes. We are going to discuss all these technicalities in the very near future.
Oh,
But you're
okay.
right.
Okay. Thank you. Thank you very much. Thank you very much.
No problem. So there is something in the chat. Let me check. What happens if C1 and C2 are real valid numbers? Well, nothing special actually, because you see here they are real valid numbers. So cosine and sine are real valid numbers. So you can describe state vectors which are real valued numbers, and in this particular case, the scalar product commutes. So if you compute bra phi and ket theta, this gives you the same result as bra theta ket phi, and there is nothing particularly special about that. But in general, a quantum system is described by complex valued vectors. Okay. And there is another question, which is the normalization condition. Does it work for the row vectors? So the normalization condition is the following. So uh, the if I have a bra associated with phi, I can construct a ket associated with phi, which is just the transpose of this, right? So I will write a column vector that is cosine phi, sine phi. And again, the normalization condition must hold. Okay. Okay, so why do we consider the complex value numbers? Because, as I said, in general, you need to consider complex numbers. For the moment, I just told you that this is a possibility, and we did not need it, in fact, but we are going to see that you need. Okay, so this is not a choice. This is mandatory in quantum mechanics, actually. So Elise, if greater than 0, you can get 1 as a summation of probability. If greater than 0, you can get. I didn't understand exactly. Is this a answer to Grace, Elise? Okay. Felix, can we say the state vector you're talking about now is pure? Yes, but I didn't introduce the notion of a pure state and a mixed state. But it turns out that there are different types of states, and as Felix is pointing out, and this is at the heart of very interesting quantum phenomena, also known as quantum entanglement. Okay. Um, are these computations defined in any inner product space, or the inner product function in the vector space may have some extra properties, or the vector space itself must have some properties? Yes, that's a technical question and a very important one. So these vectors, these state vectors, they are defined in general in a Hilbert space where the states are squared integrable functions. So what I mean by that is that you can normalize your functions or your vectors. So for us, at the moment, we are considering this two-level system the inner product has to satisfy the standard properties of an inner product, namely linearity. Also, well, in this situation where you have complex vectors as well, you have to be careful with, because it must be linear in the ket and anti-linear in the bra and so on. But all the properties of the scalar product, of the standard scalar product with complex vectors, must be satisfied. Okay. So, and typically, I mean, there is not much more that you need. But of course, if you want to do a more complicated systems, then, as I said, you evolve that to a Hilbert space, and you have to introduce all the functional analysis machinery. But we are not going to do that in this course. Then there is a question. We know from the previous slide that the probability is cosine squared. In expanding cosine theta minus phi on this slide, did not consider this squared. Why? We are going to see the squared coming in tomorrow, but you're right. I mean, so far, I'm just working with a piece of information of the probability, because with the state vector, I'm not looking yet at the probability, but as we're going to see, we are looking at the probability amplitude, which is essentially is the square root of the probability. Okay, we're going to see that tomorrow. Okay, so the normalization condition only works when we transpose to a convex. So the normalization, once you fix the normalization condition, it is fixed. So if you normalize the ket vector, then when you transpose it, the row vector will be automatically normalized. Okay, actually, the normalization condition itself means that the inner product between a vector with itself must be 1. Okay. Yeah, Elise is right, of course. Okay. So I think I answered all the questions. And since we are already over time, I will stop here. And tomorrow we continue with these mathematical aspects of quantum mechanics. Okay. So yeah, we are starting to get to the mathematics. Should we expect our assignment today? Yes, the assignment will be posted in the website at some point today. Okay. Okay, so see you tomorrow. Have a good day. Enjoy, and try to have fun with the subjects. Bye.